Good afternoon, everyone. My name is Ritish, and I'm here to talk about my capstone project. And this project is a research-based project where I came up with a hypothesis and I try to see if the hypothesis makes sense. And I then ran some experiments to in order to debunk or validate the hypothesis. And I'm going to run you through what I did. And these are the
Could you put it on set presentation mode, please? Thank you.
So this is the agenda. This is my agenda for the day. I'm going to talk about my problem statement motivation, and I'm going to talk about my related work, what I did, and my results. So firstly, I want to talk about the problem statement, which essentially what I'm trying to do with this research is I'm trying to come up with a solution to a problem, and that problem is a problem called high jerk in robotics, where the the robot movement, uh, the movement is predefined. So whenever there is a bigger shift in momentum, whenever the movement of a robot comes to an end, it is going to stop the movement abruptly so that it's going to give a small jerk. Imagine yourself driving 40 miles per hour and then hit the brakes suddenly. You feel the jerk, right? That's what happens in a very small way to these robots. So the main problem is we have to find a particular position in the trajectory, in the motion trajectory, to start decreasing, so that at eventually when we reach the end, the jerk is going to be smaller. So when I try to go through this problem, I asked a question about how we humans try to do that, because when we try to give a high five or when we try to share someone, we make a moment smooth, right? We don't feel the jerk. So there is this. So from that, I actually went on and read a paper about cerebellum and what is the role of cerebellum in our body, in our brain, which is a very integral part of our brain, and which this is related to motions. And there is also a similar neural network structure which is called spiky neural networks, where the firstly a neural network is also inspired from our brain, and this neural network uh, is different to the regular artificial neural networks, because at a regular artificial neural network, at every node there is a value. So there is an activation value which is between 0 to 1, and we try to find that activation value. But in terms of a spiky neural network, there they there is a threshold value. So only if the threshold value is met or reached, then the neuron is going to get activated. And this is what happens with our brain too. All the trillions of neurons in our brain, they won't fire at the same time, right? We only use the neurons which are used. So the reason pick why I chose SNN is the it comes from this paper, where this paper practically proved that through the spiking ability of SNNs, there is an ability of these neural networks to find temporal encoding. So basically, if the network is too big or if the network is so sophisticated enough, the in these temporal spikes, the network finds to encode some information. So there is a bigger chance of coding informations in this type of network when we compare to regular artificial neural networks. And to do that, I've also read other papers which are related to the quintic polynomial planets. And I want to talk about the quintic polynomial planet because when I said the hijack problem, right? Uh, how are they solving this in today's day? Because there are many robots and many robotic companies. So what we do is quintic polynomial planet is just that if we have an idea of the trajectory where the robot is going to make the movement, we just do the math by hand and try to predetermine the trajectory. So this is the industry standard. So what I'm trying to do with my approach is I'm trying to train a neural network to adapt to that problem. And I'm comparing that neural network to the industry standard because uh, nothing is more better than actual math itself validating. So this is my point of comparison, the quintic polynomial planets. And I'm going to compare two of the neural networks. And when I also read a lot of papers related to spiky neural networks and all the other things, I also came across a term called STDP, where this is uh, apart from the neural net SSN spiky neural network, the STDP part is my main research contribution, where basically if two neurons in a neural network fire together, they wire together. So they eventually, if a collection of neurons can fire together, they can wire together and learn something so that the neural network gets better in performing. So I try to do that and I try to check for the work, and there was no prior work compared to it. And I thought, okay, that let's try to do this for my thesis. And so what I'm trying to do here is I have three controllers. As I said, one is the industry standard, one is pure math. This is the gold standard, which I'm trying to meet. And the other two is I'm going to use a regular SNN, which with regular training, regular gradient training that we try to do with every neural network. And I also have the third controller, which is biologically inspired from humans, where neurons which fire together, wire together, and all the things. So to do to compare these neural networks, I had three evaluation metrics. One is peak jerk, how much, what is the jerk value, and the other thing is endpoint position, where zero is like no jerk, right? So I'm going to calculate how long did the network try to took to reach zero. And the other thing is oscillation amplitude, where we know the oscillation is like the movement between the parts or the trajectory. And this is my solution architecture. This is the architecture of the neural network which I'm trying to train. So simply, I'll try to encode the neural network with eight of the values, which are like the state and how the network is going to work. And I'll also have two hidden layers where those are just uh, leaky integration neurons. And this network has from the 8 to 64 neurons. The input initial 8 neurons will turn into 64 neurons, and after that the other layer is from the 64 neurons to 32 ones. And this the sorry and the HTTP timing layer is what I'm trying to do, where if a neuron A fires before a neuron B, so that means these both neurons has some connection. So the connection between them is going to get stronger. And if a neuron A fires and the neuron B doesn't even budge a lot, then the connection between them is going to get weaker. And from this 16 layers, from this 32 to layers, 62, 16 layers is going to get. And from these 16 layers, I'm going to get two outcomes, which is a binary outcome, which where I'm going to, my network is going to tell the cart to move right or left. And this is the environment where I'm going to run this. So the environment is called a CartPole, which is from OpenAI and which is actually used a lot for simulation purpose. And as the name says, it's just a cart and a pole, and the cart is going to have two options. It either has to move right or left, and eventually I'm going to measure the pole and how the pole is acting towards the cart. And if the network learns well, the pole is going to get balanced with the cart moving right or left. And I don't have any data here because I'm just throwing the network into a environment and
Sorry to
asking it
interrupt
to.
you, Ritish.
Hmm,
You have 5 more minutes left.
Okay.
for your presentation.
Okay. So I'm going to ask the neural network, I'm going to throw it into the environment and I'm going to ask it to learn through it. And that is through reinforcement learning. And when I try to uh, ran the numbers were turned out to be so good. So the as you can see here, when I see the jerk comparisons, my model worked so better compared to the quintic polynomial ones, and this immediately made me wonder if I did anything wrong, because obviously the model is overfitting here, because I think it basically learned what to do. So as you can see, it was working so better, and that's when I try to run some diagnosis and check if what the model is doing. And when I checked here, as you can see, the standard deviation is so close to zero. So the network is not deviating itself. The standard deviation of the positions is so close to zero that the network actually thought, if I don't move, that is going to give me less jerk, and it didn't work that way. So this made me realize that the way I try to train the network is different, is wrong. And what I did is I made two specific changes. One is I changed the way I train the network from reinforcement learning to advantage actor critic, where if the network does something good, it is going to get so much incentivized on that. And I also added endpoint penalties, where if the network is staying at zero, it's going to get penalized on that. And the third main important thing is I combined all the three metrics which I showed you previously into one big metric, so that the network won't overfit for one particular metric. As you can see here, it was fitting for one particular metric. So, and I increased the training capacities from 200 to 500 episodes. And I want to talk about the jerk accuracy score too. So, okay, I'll
Sorry
try
to
to skip
interrupt you,
this. Yeah.
Ritesh. You have 2 minutes left.
Okay. So, as you can see, when I made these changes and ran it again, the HTTP timing layer was still the same and it was no changes. And this basically debunks my hypothesis where whatever I did didn't work as well. But the other good thing is, when I compared with the normal SSN layer, it actually improved to 29%, and the jerk reduced. So maybe if so, these are my findings. So STPN actually debunks the layer, and the SSN layer actually works. So basically, if I try to gain for the future works, if I try to get a bigger, more sophisticated data, and if I try to change my understanding, change the way I try and train the network, maybe I can make the SNN to learn more. So these are my findings, and these are the references which I used. And since for the demo, since this is all research, I don't have a particular demo per se product to show you, but I can show you my environment which I worked in. And so basically, this is what I did. I tried to visualize only the industry standard, gold standard one, which is just math, and I couldn't able to run and visualize the SNNs thing on my machine. So this is what the network was practically trying to do. It was trying to move right or left, and it this is what math did. This is how it came to a perfect still position, and this is what I expected my networks to do. But maybe if I change the ways I try to do it, I could get that. So that is it from my time. Do you guys have any questions?
Thank you, Ritesh, for your wonderful presentation.
I have some.
Anyone in the audience? Yeah, sure. Go ahead, Akash.
Yeah, like Ritesh, as you said that the model was overfitting.
Hmm.
Was there any solutions taken for that to be accurate? Like, was
Yeah,
the
yeah,
model
that
retrained?
Yeah, that is what I did. In this case, the model was overfitting for one particular metric, as I showed in these three metrics. So what I did was I combined all these three metrics and I took a harmonic mean of those metrics. so that if something is bad, it's going to get penalized, and if something is working, it's going to get more incentivized. So the jerk accuracy metric was the thing which I tried to do to tackle with the overfitting problem.
Got it. Thank you.
Thank you, Ritish, for your presentation. If anyone else has any questions, please feel free to ask up, or we can move on to the next presenter. Okay, let's move on to next presenter, Agarsh Lakshmana. If you can please share your screen and start up with your presentation.
Sure, I'll share